I'm Brandon Rhodes. Because of the current global situation, I am talking from Ohio. But happily, thanks to the technologies that we programmers have assembled, I'm able to contribute this year to PyCon Colombia. I want to talk about the contingent build system. It's a project that I did several years ago that I think has some lessons in it that I can show you here by using some sample code. So I often use Sphinx to write documentation. Sphinx is a framework for writing documentation using plain text plus markup where you want bold or italics or a link to another document. Plain text and markup makes it really easy to write and author documents. They might look like this. You might have a little home.rst file that has a title. You just mark it with an underline and it automatically becomes the title. And in the text, you can use special little codes and backticks in order to mark a cross-reference to another document or text like 1+1 that's supposed to be computer code. You get to just type completely normal characters in your normal editor, and Sphinx turns that into HTML. Each RST file becomes an HTML file ready to be posted on your website, where the titles and links become real HTML titles and links. When you first run Sphinx, all the pages are built. Home and tutorial both get generated. But if you run Sphinx a second time, it detects that no input files have been edited, and it rebuilds nothing. If you then edit one file and run Sphinx, then Sphinx rebuilds only one target. If we edit tutorial.rst, it will rebuild tutorial.html. Sphinx saves time by skipping files whose HTML is already up to date. Sphinx, thus, is one example of what's called a build tool. Build tools have a long and august history. The very first one was called Make, or the first general purpose one. It later won an ACM award. It was written back in 1976 by someone involved at Bell Laboratories on the Unix project that was making so many of the technologies that we take for granted today. Make is still in use today. It's probably installed on your Linux laptop or your Mac laptop. The Make tool is general purpose. It doesn't need built-in knowledge of your programming language or document system. Instead, you describe a build by writing what's called a makefile. Oh, wait a minute. Makefile with a capital M? Why the capital M when Unix folks love lowercase because it's easier to type? The answer is that when the computer sorts file names by their character code, capital letters go first because in the table of characters that the computer knows, ASCII or the full list of Unicode characters, capital letters go first. This led to a trick in the early days. If you make files like license, makefile, and readme that aren't your source code, start with a capital letter, they will all get grouped at the top of the listing and not get interspersed among the serious source files in your project. Makes them easier to find. If ls on your laptop doesn't sort capital letters first, try setting lc collate equals c in your bash rc to experience Unix as it was intended. Anyway, the makefile with a capital M lists the tasks for Make to perform. It gives the output files, Make calls each of them a target. The input files, called a dependency, I guess because the target depends on the input file being there, and the command to build each target. Here's an example. Let's write a makefile to build the two Sphinx pages we saw earlier, as though Sphinx itself doesn't exist, and we needed to do it ourselves. Remember, we have 2 RST files, each of which are built to generate HTML files. If we didn't have Sphinx to do the building for us, we might write this. A makefile that says home.html is built from home.rst using one command. Tutorial HTML is built from tutorial RST using a similar command. The makefile has an elaborate syntax that, as you can see, lets you skip repeating the file names, for example, when listing the command that generates them. These 2 tasks that we just made are each a single step. Input becomes output. But build systems are often given work that is several tasks deep. Very popular use for Make when it was invented and today is to build C language projects. There, each .c file first gets converted into a .o object file before they are linked together to form a full program. 2 steps are necessary to build the binary. Makefile, therefore, has to describe 2 steps. The program depends on the list of .o files, but each .o file depends on the corresponding .c file. Just like Sphinx, Make does nothing if no files have changed. Make only builds a target if either the output file is missing, needs to be built for the first time, or if the input file has been edited, making the output out of date. Like Sphinx, when Make detects that an input file has been edited, it rebuilds only the targets affected by that edit. So if you edit sort.c, Make knows it needs to both rebuild sort.o, and then because that makes the program out of date, it also needs to link the .o files back together to build a new copy of the program. It understands builds that take several steps. Well, once you learn about Make, you will start to see little build systems everywhere. As we've already seen, the Sphinx tool has a little build system inside to decide when to rebuild HTML. Another example, Python's distutils in the standard library has a little build system inside of it. When you describe an extension module that's made of .c files, you'll notice when building in development, it only rebuilds the .os in the extension if one of the .c files has been edited. Otherwise, it tries to save you time by skipping that work. A final example, the Python interpreter itself contains a tiny build system. Why? What does the Python interpreter itself build? It builds PYC files from your .py files in order, if foo.py hasn't been edited, to save the work of recompiling it. Aside, have you ever removed foo.py but found you can still import the module foo because you forgot to remove foo.pyc? Back in 2004, I said, Python don't write bytecode equal true in my bash RC, and over the subsequent 17 years, I have never regretted it. Try it out. You might never miss those little PYC files when they're not around anymore. So, build systems are everywhere. Generic ones like Make, and little specific build systems built into tools like Sphinx and distutils and Python. But build systems for documents always seem to have the same problem: cross-references. Let's look again at the fact that our home.rst can ask to have a cross-reference to the tutorial by saying :doc: and the name tutorial, which again turns into a link in the HTML that mentions the other document's title. What if I edit the title of tutorial.rst? What if I change it from tutorial to math tutorial? What happens? Well, Sphinx will notice tutorial.rst has been edited. It will then realize that that means tutorial.html is now out of date and needs to be rebuilt. Sphinx will say, all right, writing output, and it will rewrite tutorial. All right, tutorial.html is now up to date. We can see the correct title has been written into it. There's just one problem. Check out the cross-reference in home.html. It's still using the old title. Look at that in the upper right. It still says to learn more, read the tutorial. It hasn't updated to the new title. Sphinx didn't realize that home.html depends on text that lives over in tutorial.html and tutorial.rst. And so it didn't get rebuilt. This happens all the time with document build systems. So we programmers have learned ways around the problem. You might already be familiar with them. You can touch home.rst without actually editing it to force a rebuild. Many people, before they deploy their website, rm-r, the whole build directory, get rid of it to force Sphinx to rebuild everything to a consistent state. Very common step. I often do it myself. But even though we can work around the problem, it raises a big question. Could this be fixed? Could we design a build system that understands cross-references and always knows what to rebuild? Well, I won't leave you in suspense. Yes! The answer is yes. Yes, we can. How do I know? Because I've built one. I helped write a successful prototype solution as an open source project. For their 500 lines or less book, the Architecture of Open Source Applications project asked me and computer scientist Dr. Daniel Rocco to contribute a small project and a chapter to their book several years ago. The task they gave us, write a project in 500 lines of code or less, and discuss its software design in a book chapter. We decided it was time to tackle the cross-reference problem. And so we wrote our prototype build system, which is up on GitHub, Contingent, and we named the chapter A Fully Dynamic Build System. Well, so how do you design a build system? In general, what are the parts? Well, happily, the solution is very well known. Build system design involves three basic things. A dependency graph, so it can remember which files depend on which others. A way to detect changes, to detect edits, and it needs to know how to build things in the right order. All right, first, the dependency graph. A graph, in this case, is used in its specific computer science sense to mean a list of nodes that are connected by edges. Why on earth computer scientists chose such a vague and generic word as graph to mean something so specific, I don't know. Since I usually think of a function plot when I hear the word graph, but that's what they chose, so that's what I'll go with for this talk. This is a graph. There are several ways to represent a graph, nodes and edges, in a computer program. For example, given this small graph, we might in Python have a flat representation, where we have a list of tuples where every edge is represented by its head and its tail. Or we might choose another representation, a hierarchical one, a dictionary maybe, where each key is a node, and the value lists all the other nodes that it's connected to. Graphs are so popular as a data structure, you can even choose to skip building your own representation. There's an excellent library for Python that I really like called NetworkX, which will represent graphs for you. There are whole databases today that will represent graphs and whole query languages that have been written to let you manipulate them. so this isn't something you have to do yourself. There are plenty of ways for a build system to represent the links between dependencies and targets. All right, so build system, if it has a way to represent a graph, now needs to detect changes. There are three well-known approaches. First, you can compare file modify times. This is the usual approach used by Make, distutil, Sphinx, and many other systems. You can, in Python, import stat from the OS module, ask for the modify times of two files, and check if the input file has been edited more recently than the output file was generated. You can also, if you want to be industrial strength, compute file checksums. If you want to know what kind of industrial strength guarantees are needed to build and deploy at Google or Facebook, take a look at Bazel and Gradle and how many features they offer that the original old Make tool lacked. Or you can subscribe to live OS file events using iNotify. Instead of the build system being a command you run over and over, it can be a daemon waiting for the operating system to tell it a file has changed. That's how we wrote Contingent. I use Contingent to build my website as I'm editing its plain text. And I don't want to waste time running a command. I like it to rebuild the moment that I hit save. So, there are several ways to detect file changes. If you're building a build system, choose the one that fits best. Once you detect a change, it's time to rebuild. This is a little tricky. You need to rebuild in your build system in the correct order. Why? Well, consider a very small C program made of two input files. What if both .c files have been modified? What if they've both been edited since the last time the programmer typed make? Then there's danger. If we rebuild in a random order, we might build one of the targets twice. Why? Well, if you don't give your build system any guidance, here's what it might do. It notices that both main.o and tree.o are out of date. All right, it has to start with one of them. Let's rebuild main.o first, it might decide. So main.o is regenerated. It now has a new modify time, and program is now obviously out of date. If you're not being careful with the order, maybe it's just going alphabetically, your build system might say, oh, well, next let's rebuild the program. It's out of date and it's next in my list. So program, we've now just done the work of linking the O files together to build it. Anything left to build? Asks your build system. Oh, yes. Now let's rebuild tree.o. It's also out of date. So it runs the command to compile tree.c into tree.o. Oh, rebuilding tree.o modified its modify time, and now program is out of date again. Only a second build of program, a second time through linking the .o files together, makes it fully up to date. Only building program a second time has brought our build all the way to completion. Building files in random order can make us waste time building a target several times during the same run. So there's a general lesson here for build systems. To avoid building a target twice, where there might be multiple levels to your build, wait until all its dependencies have been rebuilt. There's a well-known solution that guarantees this. Run a topological sort on the targets that need to be rebuilt to put targets after their dependencies. I'll let you look up topological sort on Wikipedia or another reference if you're interested in it. Point being, we know a way when there's nodes and arrows to figure out an order to process the nodes in so that we don't get ahead of ourselves and build any nodes before they're ready. So, putting those three pieces together, you have a basic build system design, a dependency graph, a way to detect changes, and a little bit of caution to make sure you rebuild out-of-date targets in the right order. So, what big lesson do Dr. Rocco and I teach in our book chapter about contingent? Well, I'm known for my writing on design patterns. It sometimes annoyed me to see websites that showed design patterns, old-fashioned ones, in Python, but didn't explain whether they were useful or necessary in Python. So after handling the topic in many of my talks, I started writing those ideas in a website where they could all be together in one place. So, maybe predictably, we use our chapter that describes contingent to illustrate a design pattern. We focused on how contingent represents the dependency graph. We didn't use an existing library like NetworkX because the point of the 500 lines project was to do it ourselves and show how we would accomplish it. So we used the facade pattern plus anonymous data structures. Well, what do I mean by that? Back in the bad old days, they would tell you that if you needed to represent a graph of node and edges, you need 3 classes: node, edge, and graph. A class node with accessors and attributes and tests, and an edge class with attributes and accessors and tests, and finally a graph class, you guessed it, with attributes and accessors and tests. You need to build a whole hierarchy of verbose classes. We suggested a more modern and Pythonic approach is to just have one class. You can call it graph. Well, question, if you only have one class, how does it store its data? Our answer is in anonymous data structures. What do I mean by an anonymous data structure? I mean data structures without special domain-specific names like edge or node. Because we already saw that we can use simple data structures like tuples, lists, dictionaries, and sets to represent the dependency graph. We don't need special case classes to represent data because Python has such powerful and composable data types built in. Then, having composed our representation, we can use the facade pattern to hide those data structures behind a single big class that gives them meaning. You can have a class graph that speaks the language of add edge, remove edge, find the nodes upstream of, and the nodes downstream of another node. It uses the full vocabulary of the domain. Our graph methods speak the graph domain language of nodes connected by edges, but it stores them behind the scenes using plain old Python data structures, making things simpler, but hiding that representation from the user. So that's what we mean by the facade pattern, a class which hides what's going on, abstracts what's going on, plus anonymous data structures. We argued in our chapter that this Pythonic pattern produces simpler code than a forest of domain-specific classes like node and edge. That's what we did in our chapter. But rereading Contingent's code today, I think there's a second lesson that Dr. Rocco and I could have drawn. Yes, we usually think of a design pattern as something we add to our code that it needs. But I now think that it can be just as important to see a design pattern and remove it. Here's what happened. Let's now make explicit the innovation we wanted to make in Contingent. We wanted to be able to introduce explicitly the dependency between the text of tutorial.rst that generates a piece of information, the document's title, that is then depended on by home.html. This is the end goal. Build systems usually build their graphs driven only by file names, but we wanted Contingent to understand dependencies that arise from file content that might come and go from moment to moment as the file is edited to add and remove cross-references. I now want to show an example of this with real parsing and rendering code. That raises a problem. Parsing Rst files is pretty complex. The example code would, alas, not fit on my slides. So let's define a simpler markup language that will be enough to capture the problem. Our files will be called .in that render to .out files. Most text will be copied verbatim. The only exception is that a file name in backticks will be replaced with that file's title. Well, how do we know what a file's title is in this simple markup language? It's the first line of the file. So let's look at this much simpler case. Home.in, tutorial.in, become home.out, and tutorial.out, which are exactly the same text, except that where we said backtick tutorial.in in home.in, it becomes the title of the tutorial in home.out. Happily, it's easy to parse this markup format. All we need to do is get an input text and run .split on it using the backtick to turn it into a list which is alternating pieces of normal text at indexes 0 and 2 and 4, and pieces of file name that we need to look up in the odd-numbered slots 1 and 3. So a simple for loop over the odd numbers will let us quickly and easily in the sample code find those file names. So, how can we explain to Contingent that in this simpler example, home.in needs the title that's over in tutorial.in? Every build system I have ever seen is two-phase, two steps. First, it builds the dependency graph and gets all of its arrows set up. Then it starts running the commands that will rebuild the output files. That was always the order in every build system I had ever seen. So I tried imagining the same thing. First idea was to give the framework two functions for those two phases that the build system needs to run. The first one finds the dependencies to build the graph, and in this sample code, yields a list of the items it's going to need, all the other document titles it's going to need to get its output written. Then a second routine, once the framework has gone and learned what those titles are, that will let us render the document and insert those titles into the output text. A two-phase approach. A first step to tell Contingent the dependency to target edges needed to build the graph. Then a second step, which renders the output. Then I stepped back and looked at the sample code. My reaction? Ugh! It made me unhappy. Why? As I stared at that sample code we just saw, I realized that it reminded me of something. Have you ever seen callback code? Have you ever written code inside of a callback-based networking framework where you want to say, sock, connect to python.org, and instead of it just letting you wait while it connects, it says, no, I'm a busy framework. You need to return control to me. You need to return from your function, and I'll call you back when that connection is made. So you have to pass it a second function, step 2. Step 2 then sends some data, and the framework says, whoa. You can't sit and wait. You'll block me if you sit and wait for that to get sent. How about you return from that function, hand control back to me, and give me the function step 3 that I should call. I'll call you back when that data has been sent. And then only when your third function, step 3, runs, can you finally close the socket. I don't know if you've ever seen code like that, but it happens sometimes in Python. It happens frequently in several other languages. Callbacks are so much work. All you wanted was normal procedural code like connect to python.org, send some data, and close. It could have been 3 simple lines of code. And instead, some framework forced you to atomize your code into a maze of go-tos. That's what callbacks do. Well, drat, because what have I just done? That's exactly how I had just designed Contingent. It needs each task written as callback code. First, you do some work and figure out some things you need to ask the framework for. You have to return, let the framework go collect those document titles, and only then are you ready to render. Just how bad is callback code? It's so bad that Python 3 added 2 new keywords. Python is pretty sparing with its keywords, simply to help avoid the callback pattern. Usually we think of a design pattern as something we bring into our code. Oh look, I can bring the facade pattern into Contingent. But in this case, I discovered a pattern already in my early design that I wanted to remove. It was already there, I recognized it, and want to ask, how can I remove it? Question. Well, I know how to pivot from callback network code to procedural network code. I just did it a few slides ago. I got a series of awkward callbacks, and I simplified it down to procedural code that simply runs one line after another. Can I now do the same thing with text rendering code? Yes. I can reimagine rendering like this. There's no first step. There's no 2 phases. There's no building the graph and then executing it. I simply write what I want to do. Render says, let's read from the path I'm in charge of, home.in, and let's split it apart. Let's visit all of the file names in between backticks and replace them with the title of that file name, so that tutorial.in hopefully gets replaced with its title, tutorial. Then join the pieces back together and return. What does title of do? As we said before, it reads the file content and gives us the first line. Simple markup language we've defined, puts titles on the first line. And then what does read do? It opens the path and reads the contents into a Python string. Very simple. No 2 phases, no 2 pieces, no callbacks. I've simply written rendering here the natural way that I would write it in Python. I love how the code looks when I've pivoted away from the callback pattern. But how can Contingent run this code while learning its dependencies? The code will run outside of Contingent's control. How will it know what order those routines were called in? Someone once said, all problems in computer science can be solved by another level of indirection. So let's add one. What we did in Contingent is we added a decorator, called it task, to each of the tasks that Contingent is supposed to run and rerun when the input files are changed. By giving Contingent a task decorator, it can assume full control of each build step, even though they are written as simple procedural code. Contingent can now observe the calls that are happening between these 3 tasks. Let's see how it works. We know we want to produce home.out, so we call render home.in, and the function we saw earlier starts running. Well, the first thing it does is it needs to read home.in, and because we have a wrapper that's been installed by the task decorator wrapped around that build step, we can see that render called it, and we can see what argument it was called with. So Contingent now knows that read home.in is now running. Read home.in reads the file off of disk, returns a return value, a string with the file content, and render home.in continues running just like normal. It then calls, title of tutorial.in when it sees between the backticks that it's going to need the title of that document. Contingent sees that call because of the wrapper. Title of reads tutorial.in. Contingent can see it do that. That then completes and returns a string. So title of can grab the first line and return it to the render function, which can now complete by substituting the title tutorial in at the place where there were backticks and the file name tutorial.in earlier. All right, it's now time. First, thanks to Contingent's decorator, we now know the call graph, and in the process, we've already rendered the first page successfully because there are no two phases anymore. The same phase of discovery that learns the graph is also going ahead and rendering the page for us. Let's render the other page. We call render tutorial.in so we can learn what goes in tutorial.out. Render, as before, calls read tutorial.in so it can learn the file's contents. Wait! Isn't read tutorial.in a task that we've already run? Yes, look over to the left. We've already called read tutorial.in once already. We're about to duplicate work. This is a problem specific to Contingent because make deals with files. A target only needs to be built once. The file can then be read by downstream steps over and over. But Contingent has made a crucial pivot that makes the situation different. Its nodes aren't files. They are calls. Contingent has pivoted quietly from being a graph of nouns, files, to being a graph made out of verbs. Each element of Contingent's graph of tasks is a verb, an action, a function call with some arguments. So this raises a question. Can Contingent, with its graph of verbs, still avoid repeating an action? Or will we have to read in tutorial.in twice? Answer, yes. There's a pattern for that. It can use memoization. The idea that if you have a wrapper around the function, the first time it's called, go ahead and intercept its return value for those particular arguments it was passed. The next time you see it called with the same arguments, go ahead and return that earlier return value to skip the work the second time. So we now can have render tutorial.in. When it calls read tutorial.in, we can have it reuse the value from earlier and skip doing any redundant work. By caching the return value of the first call to read tutorial.in, Contingent makes sure that this task only runs once. With this design in place, with this pivot having been made, we could declare victory. This is a complete and workable design, having wrappers around simple tasks for detecting the dependencies between text files and for running them and producing the output. So the end game then proceeded fairly simply. What does Contingent do when a file changes? It goes through its memoized cache. It removes the out-of-date return values from the memoization cache and reruns those tasks. If tutorial.in has changed, remove the result of read tutorial.in from the cache and rerun the steps necessary to learn the new output of each of those functions. Running Contingent to rebuild my blog feels magic if you're used to older document build systems. Documents are rebuilt with a minimum of work, and for the first time in my long history of using document build systems, the output is always correct. That emergency step that we always had to make before pushing the HTML to our website, rm-r the build directory to force Sphinx to go through and rebuild every single HTML file afresh from the original input files, is with a system like Contingent gone. It's never necessary. Contingent builds and maintains a complete call graph. It even understands cross-references passing between one file and another, while all the programmer needs to do to describe how their blog is built is to write plain procedural functions. So I will draw the following conclusion for us. Don't learn patterns in isolation. That only prepares you to drop in a pattern when you see a matching problem come up in some code that you're trying to write. Instead, try to learn patterns as alternatives to each other, whether they're big patterns, like do I use callbacks or plain procedures, or whether it's very simple patterns, like when a new Python programmer learns when to use a list versus when to use a dictionary. It's very useful to learn patterns as alternatives to each other. How often do you have the chance to try writing a second solution to a programming problem? It's a crucial exercise as you grow as a programmer. Often your first try isn't the best, and if you just sit down and try writing it again, you know more about the problem than you did the first time. When you don't have time to write two complete solutions, learning to prototype can be crucial to testing out different paths before committing your project to one or the other. You will be a much stronger programmer when you know not only the code you are currently writing, but how the other possible approaches would have turned out that you could have been writing instead. So that's the conclusion I'll draw from this example for us today. I know that since PyCon Colombia is remote, you won't be able to simply walk up after my talk and ask about my slides or Python or our community. But please, if you want to talk, find me on Slack this weekend. I would love to learn more about what you are doing with Python in Colombia. I am Brandon Rhodes. Thank you for listening and welcome to the conference.